Today we're going to talk about microphones. As we know, microphones are acoustic to electrical transducers. They transform acoustic energy into electrical energy through different means, and different microphones have different ways of doing it. And we're going to discuss different types of microphones and how they work, and then we'll get into the uses of microphones. And all microphones have some moving surface, which we call a diaphragm. It's excited by acoustic energy, sound waves, to move, so the sound hits some sort of a diaphragm and moves the diaphragm. That's the beginning of the process of converting that sound into electrical impulse. Three main characteristics of microphones. Microphones have a frequency response, a directional response, which we call a pickup pattern, or a polar pattern it's called, and sensitivity. Sensitivity and frequency response and polar pattern are all interrelated. When you talk about the frequency response of a microphone and its sensitivity, those are interrelated. As we discussed before, low frequencies have a lot of energy, high frequencies have less energy. So if you've got a microphone that's very sensitive, that means it's very sensitive to low levels of energy. That means that the frequency response would be higher than a microphone that doesn't. Okay, so all of these parameters are interrelated in a way, and it all boils down to what we understand about how sound works. So let's talk about the two different classes of microphones. One class of microphone is a pressure type microphone. One is a velocity type microphone. Pressure type microphone is generally an omnidirectional microphone. What that means is it picks up sound equally in all directions. We'll get into polar patterns and what that means in terms of directionality in a little bit. The velocity microphone is what we usually use in the studio. Let's talk about the less quality types of microphones. These are the microphones that are mostly used in industrial uses. For example, in the 40s and 50s, those old-fashioned telephones with hard plastic receivers that would hang on the wall, they would use carbon microphones because they were extremely durable. Not very sensitive, but to pick up voice when you're trying to communicate over a telephone line, that's why you get this kind of a tunnel sound when you think of a telephone voice. Because the microphones weren't very sensitive and not very good quality, but they're extremely durable. So what it is basically it's a small brass cup that's full of carbon granules, and it has a very thin metallic diaphragm. Here is the diaphragm in my picture. Do you guys see that? And sound waves hit the diaphragm. The diaphragm moves with the sound energy that's hitting it and takes this carbon granules that are kind of loosely packed in there and compresses them or doesn't compress them based upon a mechanical force that the sound waves hit the diaphragm with. How it works is you've got a battery going through this granular carbon and going and attaching to the diaphragm and going through. It becomes a resistor for the electrical flow from the battery or from a power source. When the granules get more compressed, it becomes less resistive to the current. So when the diaphragm pulls away from the carbon granules, they become less compressed and it becomes a greater resistance. So therefore you can take and have the voltage fluctuate based upon the resistance, and the current fluctuates. As we know from Ohm's law, that the voltage steady, but the resistance changing, then the current fluctuates with the resistance change. And that's how these microphones work. They're very crude, but it's a really ingenious way of capturing sound waves, hitting a diaphragm, and making it adjust how much resistance is in this little cup of granules of carbon so that we can detect and sort of encode what the sound wave was into electrical impulse. They're noisy, they get distorted, and they're bad frequency response, but they're extremely durable on the good part of what they do. They don't break very often. Crystal microphones. The basic principle of a crystal microphone is similar to the concept that you get from a carbon microphone. And it's bad frequency response. When sound waves hit the diaphragm, it deforms the crystal slightly and produces some electrical impulse. So, not terribly useful in the studio, but really useful for various industrial uses. Now let's talk about what we do in the studio. That's sort of why we're here. Studio microphones have two major categories, condenser and dynamic. Dynamic, in that category, are two different subgenres. At least this is how I look at it. Some people call a ribbon microphone an entirely different type of microphone, but I believe that they're both dynamic microphones, a moving coil and a dynamic ribbon microphone. The condenser microphone is probably the higher quality microphone, and both of these categories of microphones are used in the studio. The two genres of dynamics are used quite often in the studio. Let's look at a dynamic microphone and how it works. So, Michael Faraday, 1791 to 1867, during his day, the concept was that electricity and magnetism were entirely separate forces and that they didn't relate to each other at all. And he learned most of his science by setting up experiments and then looking at the results. So he didn't use mathematics and theoretical physics to project results. He would set up an experiment and say, okay, this is actually what happens, and so this is why, and then tries to come up with a reason as to why it happened. He set up an experiment, started out with a battery, and he wired it to a piece of wire, then wrapped around a compass, and then reconnected it through a switch. Closed the switch, and every time he closed the switch, the needle would start spinning. He proved that when current is flowing through a wire, it creates a magnetic field. So if current is flowing through a wire, there's a magnetic field that encircles it. And so there's a magnetic field created by the wire wrapped around the compass, and when you connect the battery, current flows, and all of a sudden you get a magnetic field, and it made the compass move. So this principle is used in industry every day. Electromagnets, for example, a junkyard with the electromagnet picking up cars and moving it and dumping them, and that's a big electromagnet that they have that just picks up metal and moves it to another place. So that principle is used in microphone design, and if you look at the picture here, you can see how it's done. You've got your diaphragm here, which is a very thin, light, movable. This is sort of the side view. So this is your diaphragm. And then around the diaphragm is connected some extensions where there's a wire wrapped around. You've got magnets that are permanent magnets sitting in close proximity. When moving air hits the diaphragm, it makes it move back and forth. And as it does that, the wires move through the magnetic field, and in doing so, it creates some electrical current. So what I neglected to tell you is that this principle of sending current through a wire, creating a magnetic field, is non-directional. So you can take a wire with no current and no voltage and pass it through a magnetic field, and it creates a current flow. And that's exactly how this works. A speaker, on the other hand, is the exact opposite. You put electricity into the speaker, it goes through the coil, and because there's fixed magnets, it makes the diaphragm move back and forth based upon the fluctuation in magnetic fields. A speaker and a dynamic microphone are very similar in many ways, the opposite of the same principles. And of course, one diaphragm's relatively small in a microphone, one diaphragm's relatively large in a speaker. One of the more famous microphones that you can find that's a moving coil dynamic microphone is an SM57, a Shure Brothers SM57 or an SM58. If you go to a live performance, you're bound to see an SM58 as a vocal mic. They're very, very common, and they're very durable because they're housed in a metal casing. And this really isn't a terribly difficult principle to understand as to how it works. Now, on the other hand, the other kind of dynamic microphone, I say dynamic because it uses nothing other than magnets and wires to create a current flow. So a ribbon microphone, on the other hand, is a little different than a standard moving coil dynamic microphone in that it's more sensitive, number one, has a higher frequency response, is less durable, and can be damaged fairly easily. You see that this wrinkled kind of looking piece of metal is actually the diaphragm. And what it is, a permanent magnet, and then there's a diaphragm, and the diaphragm is a piece of metal. So you could consider it like a wire, except it's flattened out, and it's very thin and light. And when air hits it, it moves it in a magnetic field and creates a small amount of current. So it's very sensitive because the entire diaphragm is actually passing through the magnetic field, creating the electrical flow. Whereas in the other dynamic microphone, you've got a diaphragm and you've got wire hanging on the diaphragm. You've got much more mass to move with air movement. Air hitting the diaphragm has to have a little more energy to move this system than in the ribbon system. So the diaphragm itself is a metal ribbon. And when the ribbon is moved by acoustic energy, it generates electricity. It's always bidirectional, meaning that it goes in both directions. Either way, if air comes in and moves it from either direction, it creates electrical impulse. And it's fragile, low output, and they sound really good because they are sensitive. And as I mentioned before, the parameters of sensitivity and frequency response are interrelated because low frequencies have more energy, high frequencies have less energy. As the frequencies start rolling off in energy, or should I say, the microphones themselves have a threshold of the amount of energy it takes to move the diaphragm and create a signal out. So a moving coil dynamic has a higher threshold, so it needs more energy, which necessarily means it can't have as good a frequency response as a ribbon microphone. And of course, we discussed before, all goes back to the basics of spectrums, is that when you can hear higher frequencies, things sound more lifelike because you can hear the spectrum better, which makes it sound more like what it's supposed to sound like.